Hi friends, once again welcome back in our educational channel, that is Precise Electronics. Friends, in this video lecture we are going to study Ohm's law, which gives the relation between voltage and current and obviously resistance. So we are going to study Ohm's law, then we are going to study concept of resistivity and a concept of conductivity. So in this chapter we are going to study Ohm's law, resistivity and conductivity. So first of all, Ohm's law. What is Ohm? Ohm is the name of the scientist who states that law. So this law is known as Ohm's law. What is the statement of Ohm's law? So long as the physical state of conductor remain constant, the current flowing through conductor is directly proportional to the applied potential. What is the statement? So long as the physical state of conductor means so long as the length, the cross-sectional area, then the material used, and obviously the physical parameters such as the temperature, then intensity of light, pressure, etc. When all these parameters are constant, the current flowing through that conductor is directly proportional to the applied potential. So the current is symbolized by I and voltage, that is symbolized by V. So V is the applied potential to that conductor and I is the current flowing through the conductor. Then we get I is proportional to V or V is proportional to I. Means I is proportional to V or V is proportional to I. But if this equation gets solved, we get V is equal to IR. So V is given by R into I or V is equal to IR, where R is known as the resistance of that conductor. V, that is applied potential, and I is the current flowing through that conductor. R is known as a proportionally constant. That is resistance, and this resistance is always measured in Ohm. So the SI unit of resistance is Ohm. If V is equal to IR, therefore R is equal to V upon I. So R is given by, it is ratio of voltage to the current. R, that is resistance, which is measured in Ohm. V, that is voltage, which is measured in volt, and I, that is current, which is measured in ampere. So the resistance of that material, resistance of conductor, is 1 ohm. What is 1 ohm? 1 ohm is the resistance of conductor when the current of 1 ampere passes through conductor when we are applying 1 volt potential. That means when 1 volt potential drop is developed across conductor or 1 volt potential is applied across conductor, and then the current flowing through the conductor is 1 ampere, then the resistance of that conductor is 1 ohm. So 1 ohm is the resistance when 1 ampere current flows through conductor by applying 1 volt across it, that is 1 ohm. Now we are going to study the experimental variation of Ohm's law. That means we are going to study how the Ohm's law gives that equations, how it proves the voltage is proportional to current and current is proportional to voltage. So the circuit diagram of Ohm's law is now going to display on your screen. In that diagram, it is clear that a DC source is used, mostly electrochemical cell or DC power source, power supply is used. Then a variable resistor is there, and that is rheostat. So in laboratory experiments, in laboratories we have to use rheostat to vary the voltage and current. So rheostat is used. This rheostat varies the voltage, and that variable voltage or the output of rheostat that is applied to the circuit, that is unknown resistor Rx, is measured by using voltmeter, which is connected across the rheostat. When the voltage is applied to that resistor, applied to the circuit, obviously current conduction takes place, and this current is measured by using a meter known as ammeter, that is current meter. So current meter is used to measure the current flowing through the circuit. Voltmeter is used to measure the voltage applied to the circuit. So that is experimental variation, the circuit diagram of Ohm's law. By using rheostat, applied potential varies from minimum to maximum value. It varies from 0 to maximum value. Mostly the 10 volt, 0 to 10 volt DC potential applied to the circuit instead of 1 volt. First we have to apply 0 volt, then 1 volt, 2 volt and up to 10 volt. And this potential can be measured by using voltmeter. When this potential varies, obviously the current flowing through that circuit get varies. When we are applying zero potential, initial stage the applied potential will be zero. So when there is a zero potential, obviously current flowing through circuit should be also zero. But when we increase the potential instead of 1 volt, the current conduction takes place. For 1 volt, we have to measure the current flowing through circuit. Then 2 volt, the current flowing through circuit, that will be measured by using ammeter. The characteristics of this experiment, that is voltage and current, is now displayed on your screen. So there are two axes, that is a x-axis and y-axis. On x-axis, the current is plotted, and on the y-axis, the voltage is plotted. The actual characteristics, the relationship between voltage and current is given by a straight line, and this straight line passes through the origin. So obviously the straight line indicates that current is proportional to the applied potential. Now we have to find out the relationship. We have to find out the slope of this graph, slope of this line. So we have to find out the coordinates of 2 points. Suppose coordinate of first points are I1, V1, that is x1, x1, y1. So on x-axis there is a current, so I1. So x1 is equal to I1, and on the y-axis the voltage is plotted, so y1 is equal to V1. So the coordinate of first point are I1, V1, while the coordinate of second points are I2, V2. Now the slope is given by using the dotted line. The slope is, we have to find out the slope, and this slope, the formula of slope is equal to y2 minus y1 upon x2 minus x2. So what is y2 minus y1? That is v2 minus v1 upon I2 minus I1. So slope is equal to v2 minus v1 upon I2 minus I1. What is v2 minus v1? That is nothing but change in potential. That is given by delta v upon delta I. So slope is equal to delta v upon delta I, and that is nothing but the resistance R. So R, the resistance of this graph of this characteristics, is given by delta v upon delta I. Delta v, that is v2 minus v1 upon delta I, that is I2 minus I1. That gives the resistance. The electrical resistance between 2 points can depend on many factors. The factors such as conductor's length of the conductor. Suppose this is a resistor, so suppose this is a conductor, then the resistance will depend upon the length of the conductor. Then it is depends upon the cross-sectional area. Suppose a Y region, then the cross-sectional area is measured in gauge. So the electric resistance depends upon the length, cross-sectional area, then the material which is used to manufacture that conductor, which is used to manufacture that wire, that means a conductor, and the physical parameter, temperature, then intensity of light, pressure, etc. Now the one figure is going to display on your screen. From this figure it is clear that a single conductor is used. Suppose this is the conductor. The resistance of the conductor will depend upon the length and cross-sectional area, and current flowing through this conductor, that is indicated by I. If a single conductor is used, how that resistance will depend upon the length, area, and the conducting material. The single conductor is used. In case of single conductor, this is a single conductor. In the single conductor, the resistance will depend upon the length, cross-sectional area, and the specific resistance of that material. So R is given by R is equal to rho L upon A, where R is equal to resistance, rho, that is a specific resistance of that material, L, that is a length, and A, that is a cross-sectional area. So R is equal to rho L upon A. And in this conductor, in this wire, the resistance is given by VR is equal to V upon I, or current flowing through this conductor is given by I is equal to V upon R, because in this case the resistance remain fixed. Next, if the length of the conductor increased, suppose the length of the conductor is double. Suppose this is one conductor, or this is one resistor, this is one conductor, this is another conductor. If these two conductors are connected in series, that means in this case the length of the conductor get double. This is L and this is L. So length get double, but the cross sectional area it remain fixed. So in this case, as the length increases, the resistance increases, because R is proportional to L, and as the length get double, the resistance also get double. So R is directly proportional to L. It is proportional to the length of that conductor. Next, if the cross-sectional area get increased, if the cross-sectional area get doubles, that means in this case that two conductors are connected in shunt. In previous case they are connected in series. Now in this case they are connected in shunt. That means the area is now increased. The area is now increased. In this case area get double. So resistance is inversely proportional to the cross-sectional area. So when the area increases, resistance decreases. So in this case, the area get doubles, so resistance get half. It is half that of the original resistance, that is half that of a single conductor. So R is directly proportional to the length, and R is inversely proportional to the cross-sectional area. From this, we can conclude that the resistance of conductor is directly proportional to the length, inversely proportional to the cross-sectional area. So from this it is clear that R is equal to L upon A. R is proportional to L upon A, or R is equal to rho L upon A, where R is the resistance of that material, L, that is the length of the conductor, and A, that is a cross-sectional area. And what is rho? Rho is a specific resistance. R, that is resistance measured in ohm. L, that is the length of the conductor, which is measured in meter. A, that is a cross-sectional area, which is also measured in meter. Actual unit of area is meter square. So R is equal to rho L upon A. L is given in meter, area is given in meter square. Now the specific resistance, that is known as, which is given by a Greek alphabet, that is rho, and this Greek alphabet, Greek letter rho, is nothing but a specific resistance, or it is nothing but the resistivity of that conductor, resistivity of that material. Rho, the rho, resistivity, that is resistivity. What is resistivity? The resistivity indicates the how that material opposes the flow of current. The electrical resistivity is a property of that particular material, particular conducting material, that measures, that gives how strongly that material opposes the flow of current, that material opposes the electric current. And this resistivity, that is rho, is mostly known as specific resistance of that material, the specific electrical resistance, because it opposes the electric current. So rho, that is nothing but the specific electrical resistance of material. And the unit of this resistivity is ohm meter. What is ohm meter? What is R? R is equal to rho L upon A. So what is rho? Rho is equal to R A upon L. R, the unit of R is ohm. A, meter square, upon N. So meter square upon M gives meter. So resistivity or specific resistance is equal to ohm meter. The SI unit of resistivity, that is ohm meter. Now the resistivity of good conductor. Good conductors obviously are copper. So resistivity of good conductor, that is copper, is very low. Is in order of 1.72 into 10 raised to minus 8 ohm per meter. 1.72 into 10 raised to minus 8 ohm per meter, that is 17.2 nano ohm meter. Nano means it is very low. So specific resistance of copper is 17.2 nano ohm meter. It gives a very low opposition to flow of current. While the resistivity of bad conductor or good insulator is very high. For example, air. Air is a bad conductor of electricity. So air will not allow the electric current to pass through it, and the specific resistance of air is 1.5 into 10 raised to 14 ohm meter. 1.5 10 raised to 14, that is 150 trillion lakhs, million, billion and trillion. So the specific resistance of air is very high. It is 150 trillion ohm meter, or it is 1.5 10 raised to 14 ohm meter. And because of this, the air is a good insulator. It is a bad conductor of electricity. It will not allow the electric current to pass through it. The specific resistance or resistivity of some material which are used in electrical appliances is now going to display on your screen. The first of all, copper. The specific resistance of copper is 1.72 10 raised to minus 8 ohm meter. 1.72 1.72 into 10 raised to minus 8 ohm meter. The second good conductor is obviously aluminium. The specific resistance of aluminium is 3.2 10 raised to minus 8 ohm meter. It is also very low. Then the iron, Fe, that is 11 into 10 raised to minus 8 ohm meter. It is also very low, but iron is not used for the used to construct the electric one. Mostly the aluminum and copper are used. And the next, that is a nickel, Nr. The specific resistance of Nr is 112 10 raised to minus 8 ohm meter. So from this it is clear that the specific resistance of copper and aluminum is very low. So they are the good conductor of electricity, and because of this, the copper as well as the aluminiums are used in electric cables or electric wires, which are used in our domestic electric boards. Aluminum and coppers are widely used. Friends, that is resistivity. That is a specific resistance of electrical material. Next, resistivity, that is the opposition to flow of current. But in electric current, electric circuit, the conductivity is one of the main factors. So we have to find out the electrical conductivity. What is electrical conductivity? Resistivity, that is opposition, that gives how strongly that material opposes the current. So conductivity gives how easily that conductor passes or allows the current to pass through it. So conductivity is exactly opposite of resistivity. So conductivity gives how easily that conductor passes electric current, or how easily the electric current flows to that material. That is electrical conductivity. And this electrical conductivity is always reciprocal. It is always reciprocal of resistor. And this electrical conductivity is denoted by capital letter G. G, that is conductivity, that is conductance, and that is inversely proportional to the resistance. So G is equal to 1 upon R. So the unit of conductivity is exactly upside down the symbol of Ohm. Symbol of Ohm. This is symbol of Ohm. So symbol of conductivity is exactly opposite. It is a mirror image of Ohm, and that is mho. M-H-O, mho. Resistance Ohm, O-H-M, and the symbol of conductance, the symbol of conductivity is mho. So friend, that is Ohm's law, specific resistance or resistivity, specific conductance or conductivity of material used in electrical industry, electric field, electronics field. So friends, thanks for watching this video lecture. In next video lecture, we are going to study the next topic, and that is the effect of temperature. The effect of temperature on the resistance value. How the temperature changes the resistance value. How the resistance value changes with the temperature. So there are two types, that is NTC and PTC. And in next lecture, we are going to study that NTC, PTC. How the resistance will changes with changing temperature. So friends, keep watching our video lecture. Bye, take care, and thanks for watching this video lecture. Bye, see you again.